Okay, class, welcome to the next lecture. So last time we started talking about sets and set theory. Today we are going to talk about more things in set theory. So I couldn't come up with a good title for this lecture, so it's just got everything that I'm going to do. So we're going to talk about set equality, subsets, and complements. Okay, so the first thing is that when you learn a new math concept, you often want to know when two of that thing are the same. So in this case, we want to know what it means for two sets to be the same, and this is one answer to that. So we are going to define what it means for two sets to be equal. So two sets, A and B, are called equal. And we use an equal sign for this, so written A equals B. If they have the same elements. They have all the exact same elements. So hopefully this is a reasonable definition of what it should mean for two sets to be equal. And that's one way to think about two sets as being the same. But then more formally, in the way you would use this definition in proofs is in the following way. So you would say something like this. For any x in A, well, if A and B have the same exact elements, then that should mean that if you pick something in A, it should also be in B. That would mean that every element in A is inside of B. But then you would also want the reverse to be true. No matter what you pick in B, it should be in A as a result. And if you can accomplish both of these things, then you're saying that they have the exact same elements in a more fancy way, a more formal way. So in proofs, you'll very often do something like this. You'll write something like let x be in blank, whatever set you're trying to show is equal to some other set, show that x is in the other blank that you're trying to show is equal to the first blank. So I guess here would just be A and B, and then you would also do the reverse, let x be in B, show x is in A. So that's how the proofs are going to go when you're trying to show that two sets are equal. Okay, so let's just do a really quick example, and it's going to be not very general, it's going to be a very specific example, so I'm just going to give you two sets. So here's the first, all the real numbers, but not all of them, just the ones that make x squared minus 1 be 0. That's going to be the same as the set 1 comma negative 1. So hopefully you can immediately believe that this is true, but let's try to prove it using this definition. So I'm going to let x be in the first one. It doesn't have to be the letter x, but I'm just going to use the letter x. And then I'm going to show, as a result, that x is either 1 or negative 1. So this is sort of just a guideline for more fancy proofs later. Okay, so since x is in there, then you just say what that means. So since x is in here, that just means that x squared minus 1 equals 0, which means that x squared equals 1, which means that x equals plus or minus 1, which means that x is in this set consisting of 1 and negative 1. And then you got to show the reverse direction. So we let x be in that set 1, negative 1, and then we show that it's in here as a result. So it's kind of silly to do this one, but it's a good sort of example of what's to come. Okay, so let x be either 1 or negative 1. Show that it solves x squared minus 1 equals 0. Well, 1 squared minus 1 does equal 0. And negative 1 squared minus 1 does equal 0. So it doesn't matter which one x is, if it's 1 or negative 1, it still is in this set because it solves this equation. Okay, so that's the end of the proof. All right, so now let's prove something a little bit more general and something more like you'll see. So typically when you prove things about a new concept, you don't prove specific ones, you prove properties. So here's a nice property that we're going to prove. Okay, and now I'm going to start using this other fancy word now that we're in a new subject. I'm going to call this a proposition instead of a statement. Proposition is just a statement that's more important, and it's used in textbooks a lot. So it's important, but it's not the most important. The most important ones are called theorems. So I'll start using that word too. Okay, so proposition, if A and B are two sets, then here's something that should definitely be true. If I intersect them, it shouldn't matter which direction I intersect them in. If I do A intersect B or B intersect A, they should be the same because they're just what's in common to both. But now we'll actually prove that these two sets are equal using our definition of set equality. All right, so how will we do that? Same as the previous proof, you let X be, it doesn't have to be X, whatever letter you want, be in one of the sets, and then you show that it's in the other as a result of that, and then do the reverse. So it's really sort of like two proofs. Okay, so this is why you have to get really good at saying what it means for an element to be in a set. So what does it really mean for X to be in here? Well, remember the definition of A intersect B. It really is the set of X's that are in A and B. So this really means that X is in A and X is also in B. But X being in A and X being in B, that's really, I can write that the other way too. So then I can just say, well, that means X is in B and X is in A, if I just say the sentence in the reverse direction. So if X is in B and X is in A, that tells you that X is in B intersect A, just because I said the same sentence in the other direction. Because this set is really just the set of things that are in B and A. So it's again kind of silly. All I'm doing is saying this phrase differently. So that proves what I wanted. That shows that if I was in there, then I was in here. So now I do the other way, and it's exactly the same. So let X be in this one, show it's in the other one. It's going to be just the same. So since X is in B intersects A, then X is in B and X is in A. So that means X is in A and X is in B. The point is it's in both either way. So now that's in this. Okay, so that's the end of the proof. Hopefully not too bad. So just as an aside, I might do this later, but you can also sort of think like this. So you can write down the definition of A intersect B. And then you can just sort of work with that. So saying this is basically just the proof written a little bit differently. Is the same as saying this. And that's just exactly what B intersect A is. So this technique will also be used occasionally. Okay, but the reason I wanted to do it this way is because it leads into the next definition, which is sort of like half of this definition. What happens if only one of the directions is true? So like, what if only this thing was true? but not this one. What would you call that? Well, that's the next definition. So a set X is called a subset of Y, and it's written like this, written X, and then it's sort of like a big C, but not really. I would look it up online to see better pictures of how the symbol looks. Sort of like a less than or equal to, except not pointy. Okay, so it's written like this. X is a subset of Y. But so there's a little subtlety here. So it's only written this way if X could maybe equal Y. So I'll talk about that more later. And it's written without the underneath part if X cannot equal Y. Okay, so what does it actually mean to be a subset? Well, it's sort of what it sounds like. X is inside of Y. It's a subset. It's just sum of Y. It could be all of it. In this case, you're saying that it could be the same set, but it's definitely inside. And in here, you're saying, nope, it's just inside, but it's not the same set. You're much more sure about it. Sort of compared as like saying less than or equal to. So like you could say 3 is less than or equal to 3 if you want, and that's true. But you can't say 3 is less than 3 because it's not. It's equal to it. Okay, more on that later. Let me finish this definition. Okay, so this is if all elements of X are in Y. So then that just means X is inside of Y. Formally, this is really just saying for any X in X, it's also in Y. And when you do proofs, you're going to write something like let X be in X, show that as a result of that, X is in Y. So you're just doing half of set equality. You're just showing one is inside of the other, but not vice versa. And then the subtle differences between these two things in red boxes is just whether or not they could secretly be the same set. And you just don't know it. All right, so let's do a little example of showing something as a subset of something else. All right, so how about this? Let A be this set. So the set of numbers that look like 3n plus 1, where n is a natural number, and B will be the set of numbers that look like 6n plus 1 instead, where n is a natural number. So really quickly, we could think about these better. So like, what is this really? So if I plug in 0, I get 1. So it's 1 and then adding 3 a bunch of times. And this one is 1 and then adding 6 a bunch of times, 7, 13. So if I have these two sets, maybe you can already tell that one of them is inside of the other because they have lots of the same things. So B is going to be inside of A because everything in B you can find in A. But they're not equal because, for example, 4 is in A, but it's not in B. Okay, so we're going to prove that B is a subset of A. So again, this means that I'm saying, and they're definitely not equal. So B is inside of A, or you could say A contains B. but the real way to say it is just that B is a subset of A. Okay, so let's prove it. So I'm just using the definition of subset. So I'm trying to show B is a subset of A, so that means I have to show that if I have anything inside of B, that I can show that it's an A as a result. Okay, so all we do is say what it really means for X to be in B. So what can I say if I have something in B? Well, I'm not saying it's a specific number like 1, 7, 13. I'm just saying it's some element in there. So what that means I need to do is I need to look at the set builder notation of the set to say what it is. So X is in there, so X looks like 6n plus 1, where n is a natural number. That's what it really means to be an element in there. And since I want to show that X is an A, what that really means is that I have to show that X looks like 3n plus 1 for some n, but I already used the letter n, and it doesn't have to be that. And in fact, it shouldn't be now that I've already used it. So I'm going to call it 3m plus 1. Oops, m is in n. So here, I'm just trying to get from X looking like this to X looking like this. Okay, so that's not so bad, actually. We can do that. So next, since X looks like 6n plus 1, I can just rewrite it as 3 times 2n plus 1. So now, X does look like 3 times a natural number plus 1. So since 2n is still a natural number, because it's 2 times a natural number, this means that 3 times 2n plus 1 is in the set A, and that's just X. So X is an A. And that's what I wanted to show. So this shows that B is inside of A, but maybe it still equals A. So now we have to get rid of the possibility that they could be equal. So next we have to show that B is not equal to A, just by showing that they differ in some way. And that's a little bit easier to do. We just can look at an example, a counterexample. So 4 is an A, but 4 is not in B. That means that they're not the same. So thus B is strictly contained inside of A and is not, there's no possibility that they're equal. Okay, so that's the end of the proof. Okay, so that is the subset definition. That's how subsets work. We're going to do a lot with them. But on to the next definition in the title, and then we'll try to combine some stuff together. Okay, so next what we do is this weird little trick, one trick that doctors don't want to tell you. So next we think about sets in sort of this weird context, which is that they are just being inside something called a universal set. That really doesn't do anything for us in the earlier stuff. So for example, some people might rephrase this proof I just did and say something like, at the very beginning, let n be the universal set for the problem. So you're just sort of indicating a set that all the sets you're talking about happen to live in. So both of these are just subsets of natural numbers, but you don't have to show it. You could just see that their lists come from natural numbers, so they're already inside of there. And it doesn't really do anything here, so that's why I didn't bother with it until now. But the reason we want to talk about it now is so we can talk about complements. So then we can learn about something called complements, which are sort of like negations. So it's going to be like what's not in the set. What you can't do if your set is not living inside of some bigger set. You can't really say like what's not in here because everything is not in there. But if you're in the context of some universal set, then you can talk about the stuff that's not in there, but still is in the universal set. Okay, so it'll make more sense with the examples, but I hope that makes sense so far. Okay, definition. Given. So now we're going to start by assuming that the sets we're talking about are living inside of a universal set. So given some universal set, U, where we have this other set, A is inside of U, the complement of A is just going to be all the stuff that's not in A, but is still in the universal set. So is the set of elements in U that are not in A. And it's written as this, A to the C. That means A complement. And so we could write it very formally. The definition of the set is actually the x's that are in U such that they are not in A. So it's everything else. So note that when you say something is in here, so if I say like Z is in this complement, that means you're saying that Z is not in A. Or it is not the case that Z is in A. So that's what it means to be in the complement. Okay, so let's think about some little examples of complements. So you can see why we need a universal set, because you need something to be inside of in the first place. Okay, so let's use the universal set to be R, the real numbers, so just all your favorite numbers. And let's make A be this set of real numbers which are positive, bigger than 0. So then what is the complement of this set? Well, first I'll write it in this weird way, so even though you can probably visualize immediately what it is. So it's the things in the real numbers such that X is not in A. But what does that really mean? To not be in A, that just means that you negate the conclusion. So to not be in there means that the negation, it makes the negation of the predicate be true, or the negation of the property being, makes that be true instead of the original being true. So what you're saying is that X makes the opposite be true. So X has to be less than or equal to 0. But that's sort of overcomplicating it a little bit. This is just saying positive numbers. So what are the things that are not positive numbers? Negative numbers. And also 0 is not positive. Okay. But yeah, it really comes from doing a sort of negation on the property. So I'm really just negating that to get to this, because I'm saying it's not the case that something is in there, which means that it's not the case that this property is obeyed, which means it is the case that the negation of this property is obeyed, which gets you down to here. Okay, that's the very formal way of thinking about it. So let's do another one, another specific example. So let's think about the universal set as being the natural numbers. So I'm working strictly inside of the natural numbers. And if A is the odd numbers, then the complement should be the things that are natural numbers but not odd numbers, aka the even numbers that are positive. And you could do this using fancier ways, meaning you could think of A as being the set of 2n's plus 1, where n is a natural number. And so then you're negating that property. So you're saying that the complement are the things which cannot be written as 2n plus 1, where n is a natural number. And those are just the even numbers. Okay. But again, you don't have to think that hard on this example. It's just even and odds. Those are the opposites of each other in the context of being in the natural numbers. Okay. So what about something like this? What is the complement of a union So if I had two sets and I union them together and I complement that, what is that sort of like? Well, then what we can do is we can think about our definitions more. So it's really the set of stuff that is not in the union of the two. So it's not in A union B, but what is the union? Remember, that's the set of elements which are in one or the other, at least. It could be in both. So when you're saying that you're not in the union, you're saying that you fulfill the negation of being in the union, which to be in the union means that you are in A or you are in B. And so to not be in the union means that you negate that. And then we know how negation works with logical words like and or. So it means you negate both sides of the or. So X being in A becomes X not being in A, and then the or becomes an and. And you negate the X being in B. So this is really what's said. This is really saying that X is not in A and X is not in B. Well, that means that X is in a complement. That's what it means. In fact, I should write one more step like that. This is the X's which are in a complement, because that's what it means to not be an A, and B complement, because that's what it means to not be in B. So we get this interesting thing, A complement, B complement. So this is sort of just a cool little fact, and it sort of shows you how to work with complements and arbitrary sets. So you're just negating the property, and that'll get you to what the set actually is eventually. Okay, and this should also sort of remind you of De Morgan's law, because it looks very much the same. It's like negating an logical or, and it becomes an and, where you negate both of the statements. All right, so that was sort of just like a little side thing. And it is related to the next definition, sort of. Well, actually, no. Okay, so given two sets, A and B, where they both live inside of some universal set. We can define another concept called the relative complement. And you can read it as A minus B. So it's related to complements. It's stuff that's in one, but not the other. So you're sort of like starting with A if it's the bigger one, and you're taking away the stuff that's in B if it's inside of A. So it's written as A minus B, and it's just what I said. So it's the stuff in the universe which was in A, but not in B. So right away, hopefully you can tell that you could think of it in this other way. So if it's in A and it's not in B, that's actually the same as saying it's in B complement. So then you can think about it as A, things that are in A and things that are in B complement. That's just A intersect B complement. But we like to write it like this because it gets the idea across better, which is stuff that's in A, but then you like take away the stuff that's in B that overlaps. Okay, so just a very quick example. If U is the real numbers, A is 1, 5, and 10, and B is 6 and 10, then A minus B would be the stuff that's in A, so 1, 5, and 10, but is not in B, so that's just 1 and 5. So the 6 doesn't have any effect on it because it's not in A in the first place. So first of all, it's got to be in A, and then it's got to not be in B after that. So 10 gets taken away because it is in B. Okay. And what else? So then the complement symbol you can use sort of differently if you want. So you can write things like A complement. If your A is living in some universe, which it has to be, universal set, you can also just think of it as the universal set take away A instead of just A complement. And same thing with B. So it's the same thing. Just a different symbol. Okay, so let's do something else. Let's prove some facts. So let's prove properties of these set, I'll call them operations because they're just ways to combine the sets together. So here's proposition. So let A and B be two sets inside a universal set. Then you can do this. If you do A take away A minus B, that's just going to be A intersect B. Okay. So this just gives us a way to practice using the stuff we just learned about in terms of a proof. Okay, so how are we going to show that the two sets are equal? Well, we're going to use the definition, but I want you to think about the definition and realize that when you're showing that two sets are equal, what you're actually doing is you're showing that they are both inside of each other. They're both subsets of each other. So we're going to show this, and we're going to show this. And that's equivalent to the definition of sets being equal, because the first one is just saying the first part of the definition of sets being equal, and the second one is just the second part. So if they are subsets of each other that could be equal, then they have to be equal. There's no other option. Okay, so we're going to show this. And let's do the first one first. So let X be in this thing. And then we're going to show as a result that X is in the other one. And we'll do the other direction after. Okay, so same as the proof I did a long time ago. So you just say what it really means to be in here, and it'll reveal itself to you why it should be in the other one. Okay, so what does it mean for it to be in here? Well, maybe I'll write it out. So it means that it's in the first one, and it's not in the second one. That's what A minus B means, but now my B is this whole other set. So it really means that X is in A, and X is not in A minus B. So the first part is nice. It's just an A, and that's good because I want to show that X is in the intersection of A and B, which means I got to show that it's in A and it's also in B. I've already got that it's in A now. Now I got to somehow show it's in B to be done with this direction. Okay, so that means I should elaborate upon what it means for it to not be in A minus B. So let's think about that. To not be in A minus B, what is that? That's the set of stuff which is in A, and it's not in B, right? So that's what A minus B is. But if X is not in there, what does that mean? That means it's in its complement. So it's in here instead. And what is the complement? It's the stuff that's not in A minus B. So let's write out what that really is. So it's the stuff that such that it's not in A minus B. So I'm sort of just rewriting what I wrote before. But now to not be in there, what does that really mean? That just means that the negation is true, right? So it's not the case that X is in A minus B. Sorry, I'm just sort of being too repetitive now. It seems like I'm getting all mixed up. So it's not the case that X is in A minus B. So then it's the negation of X being in A and X not being in B. That's what I want to say. It took me a while to say it better. Okay, so because that's what it means to be an A minus B. It means it's in A and not B, but I'm saying it's not in there. So I'm saying the negation of it, which means that it's not in A or it is in B. So X is in here. So this is A complement or B. So because it's not in A or it's in B. So what do we know? We know that X is in A from way up here. We know that X is in A complement union B. So that's a bit weird. Hold on. Okay, so yeah, this is weird. Okay, so X is in A for sure, and X is in this union, which means it has to be in one or the other, or both. Well, so how do you know it's in B? Because I really want it to be in B. Well, that would mean it cannot be in the first one, and it's only in the second one. But X is in A cannot happen at the same time as X being in A complement. They are separate from each other. If it's in A, it's not in A complement, and vice versa. So that can't be in there. And if it's in a union and it's not in one, that means it better be in the other. So what this is really saying is that X is in B. So now finally we know that X is in A and X is in B. So we're done with the proof. Okay, I would recommend doing that one again on your own to get a better understanding of it. All right, so now for the other direction, I gotta let X be in A intersect B, and then I gotta show that X is in A minus B as a result. Okay, hopefully this direction's a little easier. I don't think it is. Let's see. Okay, so X is in A intersect B. This means, well, it just means X is in A and X is in B. So what do we want to get to? We want to get to X being in here, which means we want X to be in A, but not in A minus B. Well, since X is in B, this immediately means something good, that it's not in A minus B, because A minus B doesn't have stuff from B in it, but X is in B. So X can't be in there because it's in B. So then we know that X is in A and X is not in A minus B, but that's exactly what it means for X to be in where we want it to be, because that set is just exactly that. It's the stuff that's in A and not in the second thing, which is A minus B in this case. Okay, so that's the proof. I didn't really like it, so let me just do it a different way now too. So that's the end of the proof, but you can also do it this way, which is you could just manipulate the sets themselves and see if that works. So let me just do that real quick. Okay, so this is what it means. This is what this set means. Stuff in A that's not in A minus B. And then I'm just gonna play around with the symbols to see if I could get it to be A intersect B. Well, this and is really the logical and, so maybe I'll write it like that. And then this is really a negation of X being in A, not B. And then this is really saying that X is in A and X is not in B. That's what A minus B is. And then I'll distribute the negation through to tell me that X is not in A and then the and will become an or, and then X will be in B. And then I can distribute that and through the or using logic that we've learned. So this tells me that X is in A and X is not in A, or X is in A and X is in B. So tell me all the things that are in A and not in A. Well, guess what? There are none, so there's none of these. So really there's nothing in that part. So there's only the stuff that's in A and the stuff that's in B. So just this stuff. Oh, isn't that just A intersect B? Yes, it is. Okay, I think that was a little bit easier that way. All right. That one was a bit hard of a proof. Okay, so this little bad boy right here leads us to something else called the empty set, which I need to talk about at the very end here. So this leads us to the empty set, which I did not put in the title of the lecture, but I've snuck in now. Okay, so definition. The empty set is it's the only set with no elements. It's a very important set though. And you can write it like this, written as that, or the curly brackets with nothing inside of them. You can't really draw nothing, you can, because there's still space in between, but that's the best you can do. And it's a very important set. We can define something else. So two sets are disjoint. Disjoint should mean that they have nothing in common, right? So their commonality is their intersection. And if that is empty, meaning there's nothing in there, then that's what it should mean for A and B to be disjoint. And so one property that we just used, but I never said until just now, is that the complement and the set itself, they're always disjoint. Because one is just what's not in the other and vice versa. So that's actually what I used earlier when I did this. What are the things in A and not in A? Nothing. It's the empty set. So it doesn't do anything. And then there's lots of properties of the empty set, but now I'm getting a bit tired, so I'm just going to do one. So here's the last proposition of the day. So for any set A, here's two properties. The empty set is always a subset of every single set that you can think of. And two, everything is a subset of itself. So the first one is not at all obvious. It's hard for people to get that the empty set is a subset of every set, but it's really a vacuous truth, which means that it's true because the hypothesis doesn't happen. So what I mean is, let something be in the empty set, show it's in A as a result. Okay, well, let something be in the empty set. Well, there's nothing there. Since X is in the empty set, all of nothing I have is in A. And it's because there is no X. So it's true when I say that everything in the empty set is in A. Yes, all 0 things that I have in there are definitely in A because there's nothing in there. So it's one of these vacuous truths. 2 is true just because If you let X be an A, then it's an A. So that's the definition of a subset. Okay, so that is it for today. This lecture seems like it was 20 hours long. Hopefully it wasn't. See you next time.